Welcome to Getting Started with Apache Solr Search Server. I'm Robert Elwell. This is Section 1, Solr Basics. In this section, we'll discuss the goals of the course, what Solr is and how it works compared to a relational database, Solr's relative strengths, and how to install Solr on your machine. First off, I'd like to get everybody familiar with what this series is about. The goal is to impart a level of understanding required to properly configure, implement, and maintain Apache Solr for an enterprise-level application. This means that the individuals who would be most interested in this series would be engineers who have experience working with web services and are hoping to implement a start-to-finish solution for search in their application, or a technological decision maker who is evaluating the efficacy of implementing Apache Solr on their software stack. A little bit about me. I am a computational linguist and software engineer with background in linguistics from UT Austin as well as the University of Albany in New York. I'm a Zen certified engineer and a certified MySQL associate, so I have a lot of end-to-end LAMP stack experience. As a professional search expert, I've implemented site search on offers.com, staff.com, and most recently wikia.com, which has a whole lot of interesting scalability issues being such a large site. I'm also a tech blogger and open source enthusiast, and if you'd like to know more about my thoughts on computational linguistics or search or any of my software ramblings, you're more than welcome to look me up online. So you may know that Solr is a search solution, but let's dig in a little deeper and understand what Solr really is and how it works in an ecosystem. It's a standalone search platform based in Java, which means that you don't necessarily integrate it into, say, your application library, but you do integrate it somewhere on the edge of your system to store specific data and return it to your actual application. Solr is capable not only of full text processing, also performing computations on data types such as numbers, immutable strings, locations according to like latitude and longitude, as well as Boolean true or false. It's highly scalable both vertically as well as horizontally, which means that you can do replication as well as sharding. And it's blazing fast because it's a long-term project with a lot of great optimizations and fantastic performance. It's also run through the Java virtual machine, which gives you additional options for things like memory management and CPU consumption. As an open source project, you can actually make changes to the Solr library code and rebuild it if it's not suiting your needs as is. It uses the Lucene search library as the engine that powers indexing as well as querying. So what the Solr component actually does is integrate the computations that Lucene performs into a service that you can then query and get information out of using RESTful XML and JSON queries over HTTP. Solr works with a different paradigm than a relational database. Solr uses documents rather than tables. So all of the documents in an index are defined by a schema specification where fields are defined based on specific field types, which are then further configured beyond the base settings of those field types. A field type can be an integer. A field type could be an English language body of text. A field type could be an immutable string connoting a title that you don't want to do any additional computation on. Fields can also be tweaked for things such as, I only want to be able to query this and I'm never going to have to get it back out of the index, so store even smaller and we can worry about recovering any of the data later. You can also store all of the data and then recover that data at a later point in time for things like highlighting matches. It really depends on your need, and there are a variety of trade-offs that we'll go into later on in this series. You can perform multifaceted queries that include more than one field as your search criteria, And you can also use range values and Boolean expressions apart from just querying text. So, to continue on this path of understanding what a document is versus, say, a table row, let's imagine that everything in our index is like a single monolithic table, and the definition is the same for every document, much like the definition for every row is the same in every table. Because of this, everything in your schema needs to be predefined depending on what data you need. This means that you can't just add a table later on. You need to incorporate it into a single schema. The bright side on this is that it exists this way because Solr does all of the computation around data normalization for you. This is actually what's going on when the index is being created. You can also leverage the power of field selective querying. That is, you can say, I only want to look at these 3 fields out of, say, the 20 fields I have defined, and it will not load in the other 17 fields, much like MySQL would. Now let's take some time to understand what's going on when we're doing a text query on Solr. Relevance is basically a way of measuring how good of a match a document is based on your query. Relevance is a score that's calculated using term frequency times inverse document frequency, also known as TF-IDF. Term frequency basically counts the number of times a term shows up in a document and divides it by the number of all terms. So if you have a 10-word sentence and the word dog shows up 3 times, the term frequency for that document is 0.3. Similarly, the inverse document frequency is a normalizing factor that basically says how often does this term show up in every document, and then that helps us determine whether or not that term is particularly interesting to the document that we're looking at. And this is done by doing a log of the count of the documents in the index divided by the number of documents containing that term. So, just to wrap it all up, relevance is term frequency times inverse document frequency as a normalizing factor. So in Solr, we perform TF-IDF, but we perform it over each field that's queried. We also add in some additional boosting factors which help us at query time or index time tell Solr that these particular fields or these particular components of the query are more important than the baseline calculation. Finally, we get the relevance for each field and then sum it up, and that's the score for a Solr document when you get it back from a query. What makes Solr a suitable technology for search in a modern web application? First off, it's super scalable. What I mean when I say this is that it can scale both vertically and horizontally. So it can be sharded and distributed among different servers performing different roles. So one thing you could do is split up all of your indices by a specific value and then bring them all together using distributed search. Another thing that you can do is introduce the master-slave relationship. So particular master is responsible for all indexing, and then we replicate to a series of slaves and query those when we want to make it available to the public. What that gives us is we're taking the performance hits for indexing, we're taking the performance hits for querying, and we are splitting them apart, which allows for a little bit better performance for both of them. It's also extremely fast. This isn't only due to the high amount of optimization in the Lucene search engine library, but the multiple caching layers, so document cache, query cache, filter query cache. There's a whole lot of stuff that doesn't have to get recomputed every time because of these caches that we maintain. It's also highly configurable, so if you have a business need, it will probably address it. And if it doesn't, you can always rewrite part of Solr for yourself to address those needs. Finally, it's backed by best practices in information retrieval over the past few decades. It's been contributed to by some of IR and search's greatest minds. It's more than just string matching, and what I mean when I say this is that it includes analysis for language, so stemming, stop word filtering, and proximity detection with some degree of fuzziness. So in this example here, you can see we want to maybe just match John walked to the store as a query, but we have John suddenly walk to the store in the document, and we want to be able to introduce fuzzier proximity detection to handle this. Solr includes snippeting, which is highlight matching for free in its standard install. It's got optimized compression for tokenized strings, which means that it's doing all of this term normalization for you under the hood based on the configurations that you set up in your schema. And it includes a lot of different components for things like grouping and faceting, getting facet counts, grouping your searches by a specific field value, and things to that extent. Solr can be compared to the MySQL full text approach, which is a kind of search that you get with a standard MySQL install. However, MySQL full text is not available for InnoDB tables, which means you can't use them in transaction-sensitive situations. It does calculate TF-IDF against the columns that you're querying, but it doesn't allow you to configure the stop words that you're looking at, and it has its own heuristic that you can't turn off to determine what's a stop word in your database. There's also really poor support for proximity, and you don't get any of the faceting, grouping, etc., highlight matching features that we were just talking about in the previous slide. Furthermore, Solr scales both horizontally and vertically for free. MySQL doesn't allow sharding in the community install. And finally, full text will read an entire row, which can be expensive if you have a very large text in that row, whereas Solr's already normalized for you approach can just grab the field that you're looking for if that's the only field that you want. So, in other words, if you're just looking for something to pull out matches, then maybe MySQL will work for you, but eventually, if your application grows, you will hit problems with speed, scalability, and robustness. So, if you're trying to decide right now between something like a MySQL full text approach and Solr, keep in mind that it will give you greater control in the long run, even though there may be a higher degree of a learning curve or any kind of configuration that needs to be done beforehand. But don't worry, because Solr can take the data that you have in MySQL and import it into its index using the data import handler functionality. It's functionally capable of most of MySQL's strengths in terms of filtering and grouping, but it doesn't do joins, and that's because there's really only one sort of table, being the document schema. That's just due to a different architecture paradigm, and it's something that is a limiting factor for some people, but once you sort of free yourself of the idea of having to normalize things for yourself, you'll come to love a single schema pretty quickly. Now let's take Solr for its first spin. Let's navigate to lucene.apache.org/Solr. You'll notice that there's a download link right here, but it's directing you to Solr 4.0, which is brand new and kind of bleeding edge as it's in alpha. So let's download Solr 3.6, which has a lot of the same functional strengths as 4.0, but none of the new stuff. We can get there by going to the Apache mirrors in the Download tab, clicking on the first mirror, and then clicking on 3.6.0 instead of 4.0. For anybody who wants to try using 4.0, they are more than welcome to. All of the functionalities that we will be discussing in this tutorial should be available in Solr 4. So I highly suggest downloading the zip version, particularly if you are on a Mac, because the .tgz compressed version actually is incompatible with the OS X version of gzip. It only works with GNU gzip. You can download that. I already have it downloaded. Now let's take a moment to briefly look at what the structure of this folder that we just unzipped is. We've got some client libraries, some contribs, various jar files, documentation on the API, and then finally an example folder. This example folder we're going to spend a lot of time in. This is because this is the default install to run all of the Solr tutorials on the Solr wiki. So it has a predefined schema and a predefined configuration. Now, how do we access this already rolled Solr instance? Well, first, we go to the desktop, and we go to the Apache Solr folder we just opened up, and we go to the example folder. Let's take a look at what's in example. We have a start.jar file, so let's type java-jar start.jar, and note that Solr is loading. It's worth noting that Solr runs as a Java web server application that is compatible with both Tomcat and Jetty, but ships by default with Jetty. So now we see that there is a socket connector at 0.0.0:8983, which means it should be available at localhost 8983. So let's take a quick look at what that looks like. And here we are. This is the Solr admin, where we'll be doing many tutorials moving forward. Now we know how to start up Solr as well as where to download it. From here on out, we're going to learn all of the cool technologies Solr has to offer. Welcome back to Getting Started with Apache Solr Search Server with Robert Elwell. This is Section 2, Administration and Configuration. In this section, we'll cover how to access and use the Solr admin interface, what files control what data types are in the index, what files control how Solr is configured, how to better understand the data in your index through the schema browser, and where to find statistics on both the index and the application itself. So now we're working with the Solr admin. It's important to understand how the admin site works because it's really kind of the central location of everything happening to the Solr instance that you're presently running. So first, let's take a brief minute to understand exactly what's being linked to here. We have the schema, which links to the basic document setup of any document in the index. We have config, which explains exactly how everything is configured for your particular instance of Solr. Analysis, which allows you to understand how terms are being analyzed within the fields that you have set up. The schema browser, which describes what fields are available and the statistics against them presently. Statistics, which provides more broad information about what's in the index and how the instance of Solr is behaving. Info, which tells you some basic Java details about what's going on under the hood. Distribution, which tells you a little bit more about what's going on software-wise, sort of what version of Solr you're running, things like that. Ping, which allows you to make sure that Solr is running without doing any additional queries. Logging, which gives you options for how to set up what gets output and where to give you diagnostic information. Java properties and thread dump, we don't necessarily need to go into because it's a bit more of an advanced topic. If you're just setting things up, you're not going to run into a need for that too much. The full interface allows you to do a little bit more when you're actually querying your index. And then finally, this assistance section is really useful. It gives you a link to Solr documentation. So as I had pointed out, there was a wiki link on the Solr homepage. You can get to the same homepage through this documentation link. There's an issue tracker that gives you a list of all existing features in Jira for the Solr project. You can go through that and see if you're having a problem that has already been reported. You can send an email that basically allows you to send an email to an address that you configure, so I wouldn't be too worried about it if you're the only person touching this. And if you're not, then you might want to set up some other communication methodologies because you never know if this is going to work. And then finally, Solr query syntax, which gives you a link to the Solr wiki and describes how query syntax works. We'll talk about that in a future installment. Finally, current time will tell you when the page was accessed, and server start at will tell you when the server was started, which is useful to know in case you have any questions about did the server get shut down and then restart because I'm using runit. Let's take some time to get to know the schema file available in Apache Solr. This schema file helps us declare what exactly a document looks like within our index. So, in order to view this, I clicked on Schema within the admin, but this is actually just a prettier way of looking at the schema.xml file within the example folder's Solr conf folder. So, let's take a look at schema.xml, and we'll note that it's the same exact document. My suggestion is that if you're not going to make any changes to access it this way, otherwise, it's a little more difficult to read. So, the first section under the root schema node is a types node. These declare field types, which are used to basically transform data that you're sending to Solr into different ways of storing the component terms of that data. So, for a given field, for instance, if you pass it to a string field, then there will be no transformations. The whole value that you send to that very field will end up being that single term within the index for that field. So it's different for pretty much every field type. So for instance, Boolean, the terms are true or false. Binary, it's base 64 encoded strings. And then we move on to different versions of integer, float, long, double, really different ways to store numbers based on different trade-offs between do I want smaller index or do I want a faster query, right? Some of these are a little bit more targeted towards range queries. Some of them are a little bit more targeted towards, fewer tokens, index per value, etc. We also have fields for storing dates, which have to be stored according to the RFC for dates with the trailing Z. And now we move on to the more interesting field types, the ones that we should be more concerned with, which are the text-based field types. So there's a class called Solr text field, right? And by itself, all it really does is take a huge blob of text and stores it as a single token within the index. What we do in order to make that more useful is we pass it different analyzers. So the analyzer definition for this one basically says we want to tokenize on white space. What does tokenization mean? Tokenization is, for instance, splitting up this 13-word sentence into its component words for storage, rather than storing the entire sentence. However, no additional normalization is done for this very simple field. Whereas, in text general, we have a little bit more advanced of an analyzer that's declared here. For instance, we are specifying different behaviors during index time, that is, when Solr receives a document for indexing and processes it, versus query time, which is when we are actually trying to match against a field during a search once a document has already been indexed. So during index time, we are tokenizing basically on white space and a few other sort of obvious tokenizable characters. And then we are filtering against stop words. The stop words are specified in a stopwords.txt file in the same directory as schema.xml. From there, we apply a lowercase filter, which normalizes all of the tokens into their lowercase version, which means we won't have different terms for capitalized versus uncapitalized terms. Then we have query time analyzer, which allows us to also expand our query into different synonyms that we have specified in the synonyms.txt file, which allows us to map certain words to other words and then have broader searchability. So with these kinds of fields, we can sort of go to town on different types of analysis. Here is a text field that is specifically set up to analyze English text using different filter factories that are specified for English possessives as well as verbal inflection. We have a variety of language-specific filters that end up allowing us to declare, for instance, an Arabic field type, and even a field type for Basque based on the native classes within Solr. Again, if you find that you don't need any of these, you're welcome to remove them to make it easier for you to read your schema file. Because, let's face it, these are a lot of foreign language analyzers you may not even use in your application. So moving right along, after all of these field type declarations, we get down to field declarations. Now, fields specify what exactly you're going to have within your document. So, this document has an ID of type string, which means everything in that field is a single term unto itself. It is indexed, which means it is stored and queryable inside the index. And then we have stored, which means that you can actually retrieve it from the index. So if I say I want to see the field ID for a field with the ID of 123, searching for field ID 123 will only work if it's indexed. Being able to see that the field ID is 123 will only be available if that field is stored. Omitting norms allows us to remove certain calculations associated with length normalization, which allows us to save some memory and also allows us to skirt a couple of issues associated with longer documents getting less relevance than shorter documents. So then we also have options for whether or not a field is multi-valued. In many cases, we can make a multi-valued field include things like multiple categories, as we see here. So if something is in the category of hardware and it's in the category of consumer electronics, then we would pass that field with basically two subnodes within it in XML that would state, these are two different fields. Term vectors, term positions, and term offsets are values which are required if you want to be able to, for instance, do match highlighting against a given field. But you can set them to false if you want to slim out your index. Moving along, dynamic fields give us the option of specifying a wildcard name and then not having to actually store a definition in your schema for a specific type of field. So if I want a text general field that's indexed and stored and multi-value, then all I need to do is submit a field with the name of whatever underscore txt, and it won't complain. However, if you don't match a dynamic field naming scheme and the field is not in your schema, then Solr will complain when you try to index something that has that kind of data in it. So, now that we understand dynamic fields, we can move out of the fields node and take a look at a couple of additional components of the schema. Unique key allows us to identify a given field within a document that says this document's field here tells us, this is the one document with that value. There can only be one document. If we submit another document with that value, then we will overwrite it. If we don't have that field, then we'll complain because it should be required. And that's good because this helps enforce sort of one-to-one relationships between, say, a row in a relational database and a document. So copy fields allow us to copy a source field to a destination field. If we want to have multiple copies from multiple sources to the same destination, we have to make sure that it's multi-valued, or else Solr will complain when we try to index. What this allows us to do is specify two different methods of analysis for two different fields, and then store these fields calculated different ways and having different terms in different places. So, for instance, if we wanted to have a robust way of searching, we would obviously search against the text field. But if we were only interested in the categories, we could search against the category field and have a slightly stricter way of searching the queries that you send in, as opposed to perhaps a more robust analysis of the queries under the text definition of the field. So now that we understand how schemas work, we can add a field of our own. So let's go back down to the fields node, and we have a category field, so for the sake of argument, let's have a category 2 field. So I'm doing this because if I added the same field twice, Solr would complain. And that would not be any good, because then we couldn't use our index at all. So now that I have added in the new field, in order to make it work, I have to send shutdown command to Solr and then restart it. So note that we haven't had any errors here. I refresh, and I see this in the schema field here. And now, not that I have anything in it yet, but I could do this, and it won't complain, as if I don't have a field with that name. So now we understand what is within a schema file and what changes we can make to it. So now let's take a brief moment to go through the config, which is available on the web interface. The config can be found in the same exact place as the schema is. So that's solrconfig.xml in the conf folder under example Solr. So not to go into this too much, because there's a lot of complex settings here that the basic user will not really need to touch. But it's important to know that these are all here and that they are well documented in comments so that you can understand what you might need to do in order to provide additional support for different analyzers or request handlers you may need, as well as understanding optimizations to improve things like query time, index speed, and size of index. So, real quick, just kind of a whirlwind through. This is important because this includes different directories so that you can actually use different available class libraries that come by default with Solr, so not all of them are loaded. For instance, I had to include some extra stuff so that we could support Polish on our site. And this is the location where I had to start including the libraries. So you have configurations for how we're indexing, sort of what optimizations we're using. Really, it comes down to size, speed, and query speed. So size of the index, speed of query, and speed of indexing, and sort of pick 2 or pick 2.5, depending on how exactly you set up your index configurations. The update handler basically controls settings around receiving index commands and what to do with them. The query node here handles some configurations around querying the index. The request handlers are important to understand because they relay specific handler classes to subdirectories under localhost :8983/Solr. So you have request handlers for select, which is basically any of the searching you're going to be doing is under the search handler using, the select folder. Browse also uses the search handler, but actually presents a graphic user interface using the velocity response writer, which is configured here. So the difference between just getting the data back and an interesting GUI is basically all of these different configurations. So other request handlers such as update and the various formats with which you can update it outside of XML, which is the default. A little bit of analysis. Admin is also basically a Java class in the various handlers. And so is pinging, so is dumping request contents, spell check, and there are a lot of different configurations you can do to make spell check work just the way you want it. There's clustering available now in the later versions of Solr. Terms, which will describe to you certain terms for a given set of queries, what have you. Elevation, which makes certain documents more important than others just by the fact that you told them, I want that document to be the most important. And then response writers to handle content type settings and things of that nature for when it's actually writing out the response based on the format you request. And so you don't really have to worry too much about making changes in this, but it's important to know that all of these configurations are there, and there may be some cases where you might need to modify this for your particular needs. Another useful feature in the Solr admin is the schema browser. So what we have here is, first off, some basic schema information. So it'll tell you the unique key, the number of documents currently in the index, the most documents it's seen for this index, the number of segments, and segments are a way of storing the index in multiple files. Has deletions will tell you whether or not there are any deletions slated. Last modified, of course, the last modified date for the index, and then some directory information and what classes are being used on that directory to sort of handle the files. So now let's take a look at this sidebar here. Fields will list all of the different fields that are currently set up in your schema, and this is the default fields that come with your schema when you install Solr from the Apache site. So let's take a look at some of these. This gives you a more graphical way of understanding what fields are in your schema without having to just read the XML. So it'll tell you the properties. Is it indexed? Is it tokenized? It'll figure out what analyzer is there to know that it's tokenized. omit norms, which is a sort of advanced feature you don't have to worry about too much, having to do with normalization. And then sort missing last, which is an option that, sort of keeps things that don't have that field from showing up. It'll then tell you what analyzer is used at index time and what analyzer is used at query time. Sometimes these can differ for certain different kinds of needs. Author is another good one to look at. It's using text general, so we understand that's, really basic processing using tokenizer chain analyzer. But let's look at that category 2 we had introduced earlier. This is using text en, so let's click on text en. So this brings us to the field types category in the left nav, and gives you some explanation about what exactly text_en is as a field type. Dynamic fields is also useful to look at because it will tell you what dynamic fields exist and what properties will have if you attempt to create a dynamic field. So now we understand what is available to us in a much more graphical manner than just having to read XML. The web interface also contains resources about statistics and information. So let's take a look at the statistics. This basically will tell you all kinds of information about what's going on in your application. Most importantly, it will tell you whether it's caching. It will tell you the number of documents currently in the index, the most that it's seen, a numeric version of the index, which is useful for understanding the iterations that it has gone through. And then the last time the index was opened, it was registered, how long it took to warm up, which can be significant depending on how large the index is. And then it also lists the query handlers existing in a way that's a little bit easier to read than in the config file. So these will also give you statistics on these handlers, the kinds of requests that they've received, and any errors that they have run into. Another useful point of data available for all of these request handlers is average time per request and average requests per second. So once you bring your actual Solr instance into production, you're going to really start seeing this sort of be important to look at when you're diagnosing things. So let's take a look now at the info component. This one is really kind of super technical. So if you're working with any specific Java classes, if you had to compile your own version of Solr, then this might be what you want to take a look at to understand exactly what's going on with all of the interworking components. It's highly unlikely that you'll need this, but it's good to know that everything is here to tell you things like what revision your specific handler is at. Maybe you have a bug and you can download a patch from the Solr Jira. These things happen, so it's important to keep that in mind. Another useful resource that we have in the admin is the logging component, which will tell you exactly what is being logged and the priority that it's being logged in. So you can set this up yourself for anything that you think particularly needs a special diagnostic info. Welcome back to Getting Started with Apache Solr Search Server with me, Robert Elwell. This is Section 3, Manipulating the Index. In this section, we will discuss how to add documents to the Solr index using the update handler, how to update documents or delete them from the index using the update handler, and using the data import handler to transfer data from other sources. Now that we have our Solr instance up and running, we need to get data into the index. You can note that we don't have anything in the index now, because if you go to the statistics view, you can note that numdocs is 0. You can also perform a search on this query string, which basically will match any document with any field. So as we can see, there are no documents available to us. So the Apache project has had the foresight to add in some example documents for us to work with when looking at the example setup. So you can note these in example docs under the example folder. So let's take a look at a few of these. First off, a good one to start with would be iPod. So let's take a look at iPodOther.xml. So, as you can see, the document begins with an add tag, and then follows with the document's definitions as they are shown. So, the field values are named by the name attribute, and the values between the field beginning and end tags are the actual values for these fields. Note that an add command includes a closing tag for the add node. This basically says add these two documents to the index. We also have in this example post.jar file, which is responsible for posting data to the index. You can also use this for your own XML if you don't feel like writing your own library to handle actually opening the request and sending that along. So we can use java-jar post.jar iPodOther.xml, and that defaults to localhost. If you wanted to send it to a different URL, you would have to do -d, capital D that is, URL. So this is shorthand basically for -d URL equals http:// localhost /solr/update. Same deal. So let's take a look at what we have in info now. Actually in statistics. So number of docs is 2. Let's do this same query again and see what we get. So now we have some more results in the response. Now that we have documents in our index, now would be a good time to understand what's required to update or delete a document from your index. First off, let's perform this basic wildcard query to see the documents that are in our index now. As you can see, we have 2 iPod-related items, both from Belkin. So, first off, let's take a look and see if we can change the name of this Belkin mobile power cord to something a little bit different and see what happens. So, we were using iPod other. Let's copy that into iPod modified.xml and make some changes. So now we see the Belkin mobile power cord with dock. Let's just change that to Belkin mobile power cord. We can also change one of the features to 12-inch power cord. Now, let's remove the other document from this copy so that we're only changing one document. It's worth noting that this works because we have a unique identifier under the ID field. This allows us to submit an add command for a single document with a given ID and force the index to update that document by default. So let's try to send this document to our index. So that worked. Now let's refresh our query and see what we have for this particular ID. So here are the changes that we've made. Belkin Mobile Power Cord, and we made some changes to the features. Now, let's say we want to delete this one from the index. In order to do this, we can use the same basic XML setup. However, instead of add, we use delete. And instead of providing every single field for a given document, we can do this by query. So, as you can see, we're sending out a delete document with a query node on the inside, which basically says delete anything that matches this query. Because the ID field has a unique constraint against it, we know we're just deleting that one document. So let's send this again and see if that document is in our index anymore. Now we only have one document in our index, and it's the one that we didn't touch. Let's go back to the admin and see some other statistics about the change that we made. So, number of docs is now 1. Maximum number of docs is 2, because at one time we had 2 documents in the index. Now we know how to modify and delete documents that have already been indexed. While Apache Solr accommodates the XML or JSON-based document updating, there's also the opportunity to integrate Apache Solr with your existing database architecture. In order to understand this, Apache Solr has included in its installation an example data import handler. So let's take a look there. Right now, we're in the Apache Solr example folder. Let's go to example-dih and take a look at the README. This is important to peruse when you're following this example because it's a little bit tricky. So first off, we need to start the data import handler instance and then access a specific URL, providing a full import command from the core named DB, which is basically set up to perform a database-based data import. Before we start with this, let's take a look at what's inside the DB folder. So, we have configurations set up, and this looks like what you would see in the other example configuration, except we have some special data import handler items in the configuration. So here we have a data import request handler with configuration mentioned. Let's take a look at that configuration. So this is what the basic setup for a data import handler configuration looks like. For your needs, make sure to take a look at what's in your database, get a feel for what your schema is, and craft a schema that can then have easy ETL from your database to a document. Basically, what we're performing here are a variety of select statements, which then handle generating fields for a single document. So now that we have a basic understanding of what we're doing, let's walk through the README. It tells you to run from a different Java home the basic Solr command to run. So java-jar start.jar with the solr.home value set special. Now, what's the next step? The next step is to access this field. But first, we might want to take a look at what's in our index already. Now you'll note that even though you're used to going to this admin page, nothing is happening. Why is that? Well, it's because there are 4 cores set up for this example, and we want to look at the database core, which is specified by DB. So let's take a look at statistics and see what's in our index. numdocs and maxdocs says nothing. So now, let's perform the full import command. As we can see from our logs, a lot of stuff just happened. We can take a look here and get a response that basically says, this worked. Now, let's go back and take a look at our statistics. We now have 16 documents in the database, and they are all created by this data import handler technique. The schema, of course, is a tiny bit different from what we were working with before, but it does seem to work just fine. Now we know at least the basics of using the data import handler. For more details on this, I highly recommend reviewing the wiki on this at the Apache Solr website. Welcome to Enterprise Search with Apache Solr. This is Section 4, Querying the Index. In this section, we'll discuss using Lucene query syntax to access documents through Solr, the schema of response formats received from Solr, additional parameters that can alter responses for identical searches, and the robust Dismax query parser. Now that we understand how to add documents to our index, it's a good idea to learn how to query it. First off, it's important that we remove the iPod modified.xml file that we created in the last video. Next, let's add all of the different XML files in the example docs folder by calling java-jar post.jar on wildcard.xml. You'll note that this actually ends up committing these changes for all of the different XML files. Now, let's do a wildcard query and see what's in our index. We have 21 documents, and it's a variety of electronics-related documents that include things about iPods, connectors, hard drives, various other things. So, now that we have this sort of data, let's see if we can't just type something in and see something show up. So, let's type in iPod. We know that there are documents that say iPod. So, of course, we have a bunch of different results. And these all have to do with iPod-related things. Now, Solr uses the Lucene query syntax. However, if you don't specify a field and add a colon at the end before your query term, it will perform some default behaviors that it's worth taking a look at. So, if you want to take a look at your Solr comp folder and take a quick peek at the Solr config.xml, you can go to your select request handler, and you'll see that there is a default field being specified, which is the text field. Now, if we look at schema.xml and go all the way to the bottom, you'll note that there are a number of copy field parameters that are basically saying, take these fields and copy all of the text onto them. So now, when we enter any old search term, we're actually searching a bunch of different joined fields. However, maybe we only want to find results in the category. So let's say we want to find something in the connector category. Well, that didn't work. How about in the name field? Surely Something said connector. So where was it? It was in cat. So let's go back and try again, using cat:connector. That works. So it's very important that you know whatever you're searching against actually has the kind of values you're looking for. So, another thing that you can do when using the Lucene query syntax is perform disjunctive queries. So, cat connector, or name connector, or price is, let's say, 60. But we got at least 2 results here. Going back to the price topic, we actually support something called range queries. So, if I wanted to say anything between 0 and 100, I would use square brackets, capital letters 2, and the 2 values on either side of 2. So now we have all documents that match a price of 0 to 100 for the price field. We can also say price 0 to 50. Note before we had 7 documents, and now we have 5. So 2 of those documents were actually greater than $50. Another thing that's worth noting is that you can put in parentheses different values, and that's treated as non-proximity but same field queries. So, if I do this, we don't get anything. But if I do this, we do get something. This is because the cat field happens to be of a string value, and is therefore not analyzed. Now going back to our disjunctive query, we have things that match iPod, or things that match hard drive. Now is a good time to introduce you to the concept of boosting. Note that the iPod one was pretty far down on the list. If I give it a boost of 10, let's see what happens. Now it goes to the top. Boosting is one way that we can forcibly manipulate the way relevance works. Now we understand some basic approaches in querying the index. There is a great number left to understand, but with these basics, we can really grow off. When we query the index, we get an XML response back. Let's take a look at that response and understand exactly what's showing up. First off, we have a response header. This includes a status value, which basically tells you whether or not there was a problem during querying. Sometimes non-zero status will come back, and that will often mean you should check your error logs. The queue time value basically lets you know how long it took to query the index. This is in milliseconds. Next, and perhaps most important in the response header, are your parameters. Indent on means that we are basically pre-printing the XML. Start being 0 means that we're starting at the 0 most relevant value. Q is the query. Version is basically the version that we're using for this kind of format. And rows basically tells us how many documents we should expect back in the doc node of the response. So, the result node, which is named response, will tell you the number of documents matching your query and also let you know that it is in fact starting at the 0th result. Every single node in the result node will be a doc. Docs basically match up to your schema definition, and for all requested values, requested fields, you will receive all of the values for those fields. This will allow you to utilize that data in your search implementation on your site or other application. Now let's see what happens if we manipulate this query string right here and say, I want 20 rows. As you can see, our list of documents is much bigger. In this way, we're able to paginate by grabbing offsets with specific row limits at a time. There are a number of additional parameters that are provided in the admin interface that are worth understanding before we want to move forward with any kind of an API treatment. Let's take a look by clicking on Full Interface in the default admin page. So first, we're querying the select request handler. There are a number of other request handlers which we'll go into at a later time. Query string is the string that we were passing on the default admin page. Filter queries allow you to perform a post-processing query on the result set that you retrieve in order to further narrow what you're looking for. The start row allows you to say basically which page you're on. So if you were to provide 10 here, you would actually get page 2 greater than 10 document result set. The fields to return here, the star basically means all stored fields will show in the document XML, as well as the score. Sometimes it's a good idea to only select the fields that you're going to use, because if you're using a very large document, then chances are it will cause some performance problems. The output type is usually XML, but you can also select JSON. By setting debug to enable, you get basic rundown of every single calculation performed to achieve the score in your document set for each document. Debug explain others will allow you to select one or more documents based on a query to give an explanation of why they did not show up in your result set. Enabling highlighting will allow you to actually retrieve matches to your documents, which will give you the opportunity to provide snippets in your application. So first off, let's try filter queries. Let's select everything but require category hard drive. So note that even though we selected all 21 documents in our set, we actually only end up with 2. It's also worth noting here that the field name has been provided, as well as an FQ value for filter query. This can also be noted here in the queries. So going back, we can remove this and note that we have all 21 documents again. If we wanted the next 10, we would simply add start row equals 10. And here we are at the 11th document. So let's try to enable highlighting. Let's say we want to perform a search against features. See if we can't find something to highlight. Now it looks like paginated too far. Always keep in mind that this is a risk that you take when using this kind of interface. So let's take a look. We have resolution here, and we have resolution here. One's for a display and one's for a printer. And as you can see, we have, after our result node, LFT node, with the name highlighting, that includes values that reference the ID of each document in the result set, and then selects the appropriate field and highlights the term that we searched against. This is really useful for snippeting. Now we understand a handful of advanced parameters that we can use to better obtain data from our search index. While it's a good idea to know how to use the Lucene query syntax, it's not generally a good idea to allow user-provided queries to be fed into the Lucene type syntax. This is because users can provide all kinds of characters that may break the way the Solr query syntax works. Because of this, Solr includes a Dismax family of query parsers that allow a more robust approach to the data fed into your search. So as you can see, it not only supports the query parser syntax, but it also supports a number of parameters that would allow you to force things such as which fields to search against, what kind of proximity we should be worried about, and additional scoring measures such as boost functions, both additive and multiplicative. So let's take a look at a couple of examples and understand how the Dismax query parsers work. So first off, we should be using the select request handler and specifying the eDismax query parser under the def type parameter. First, let's do a query for iPod and see what happens. As you can see, nothing shows up because we have not specified any kind of a field. So, let's specify the feature and name fields as our query fields, and note the different documents that show up. Isn't it interesting that the actual iPod is less relevant than the accessories? This is for the simple fact that the iPod document has a lot more text, but doesn't mention iPod for that much of the text in comparison to these less relevant but less textual documents. This skews TF-IDF. So let's look at a couple of ways we can fix this. One way is to add a boost function. So we can add additive boost function, which takes the value that we're providing here, the popularity field, and adds it to the relevance. Another way is to perform a multiplicative boost, which actually multiplies the relevance times the boost field you provide. There are a number of other ways that you can do this, such as mathematical functions. However, we won't go too far into that. It's well worth your time to review what you can do by reading the Solr wiki. Another useful thing to note is that in the QF parameter, we can actually perform boosts. So, feature caret 10 means we want to give a boost of 10 to the features field. Note what happens if we add the boost field popularity. We actually have the iPod document not in the #1 position because the features field for the mini USB cable actually includes the term iPod. Now we understand a little bit more about Dismax query parser, which allows us to better parameterize the kinds of approaches that we take to querying the index while giving a more robust treatment to user-provided input. Welcome back to Enterprise Search with Apache Solr. This is Section 5, Understanding the Document Schema. In this section, we will discuss available field types native to Solr, configuring textual field types using analyzers and filters, the correct format for and best practices relating to the document schema, and how to alter the document schema file. Before we can get to work customizing our Solr install for our data, it's important to understand more about the schema file. You can access your schema file by either going into example Solr conf and looking at schema.xml, or you can look at it by accessing the schema section in your admin. I would suggest doing the admin schema section if you're only going to be reviewing values, because it tends to be a little bit more readable. So now we're in the schema file, and you'll notice that the first node is called types. This lists all of the types that have been defined based on specific classes in the Solr library that define data types from which we will be indexing values. So for instance, the string data type will take the full string of whatever you put into your document and store it as a single unique term. So if John went to the store was stored in 2 different locations, you would only be able to find it by searching for John went to the store on a string field. Boolean, again, this is just true or false, but the gotcha here is that you're passing the string value true or false. So please keep that in mind when sort of tailoring Boolean fields to your application. Going down a little bit further, here are our numeric values. So we have integer, float, long, and double, and sort of the usual values you might expect to go in there. So if it's got a decimal point, you're going to want float or double. If it's a very long integer, you'll probably want long. Another thing to keep in mind here is that we are storing these as trees. That's the special data format tree and not the binary tree. So one of the points of granularity we have for this field is precision steps. So by setting a different precision step, we are making a larger index but faster range queries. So for fields that you would want to perform range queries on, you may want to consider using the T variation of these numeric types. We also have dates, and the same thing for the date field. So we're looking here, we have some precision step information added, and if we want to do date range queries or date faceting, we may want to consider those. So moving further along, we also have plain numeric fields instead of using tree-based fields. They don't have the same robustness, but there are some values to it. Similarly, we have a special field type that's targeted just towards being sortable, which is nice if you're going to be sorting by values rather than by relevance. We have a random sort field type that allows us to perform random sorting on different documents. And finally, we're getting down to our text fields. Our text fields actually are going to be the most interesting because they're the most configurable, and let's face it, a lot of this other stuff we could probably just get out of a database. So text fields are defined by implementing the Solr text field class and utilizing one or more of an analyzer that contains tokenizers and filters that transform text into normalized terms. We'll talk more about the behavior of all of these analyzers when we get to the analyzer and filter video. So basically, each field type here is declared to have different term normalization based on the language and the different needs. So whether or not you need to do a strong match on hyphens and things like that. There are also field types for things such as phonetic pronunciation and lowercase, points in a matrix, and geospatial for location. Finally, in these versions of Solr that we're looking at, there are fields specifically tailored towards currency, which is nice if you're doing anything financial. And finally, there's a great deal of internationalization opportunity here, just native to the default example schema. So we have plenty to go over once we look at analyzers and filters. So now we understand the kinds of declarations that are determining what's available to us when we're actually planning out our schema. From here, we can declare all kinds of different fields that we want to use for our own version of our search index. Now that we have a basic understanding of what kind of native formats are available to us when creating a schema, we can dig deeper and look more closely at what's available to us to configure a Solr text field to whatever we want it to do. So, the way that we perform this is by defining analyzers inside of a field type node. As you can see, there are two different ways of defining analyzers. First off, a single analyzer will be registered at query and index time, meaning that when you're trying to match up a term, the same normalization occurs during indexing as it would during query. So you're basically feeding in text that gets normalized and then matches up against normalized text in the same method. However, you can declare different analyzers for indexing and querying, which means that you can normalize your text in a different way index time than you can at query time. So one example here is that we have an index time analyzer in the text general field that tokenizes, and tokenizing is a behavior that basically breaks up words, often based on white space as a delimiter. Next, we pass the terms that have been broken up through a filter, which basically removes anything that matches that filter. This is a stopwords filter. Stopwords is actually defined in the stopwords.txt file in your conf. So, depending, some installs include a set of stopwords and some don't. For instance, this one doesn't, but if I wanted to add a stopword, I can just go down here and type the, and now the would be removed from normalization. And then finally, another filter transforms all text into lowercase so that there's no difference in case for terms. This means that capital D, capital O, capital G, and lowercase dog both end up as the same term in the index. This is important for robustness in search. So now, looking at the query analyzer, we have much the same. We have the tokenizer factory, we have the stop word filter, And now the sort of curveball is that we're also comparing synonyms. Again, synonyms are defined in the synonyms.txt. This one actually does have some detail in it. So we can see that specific terms have been assigned synonym transformations or mappings and synonym grouping. You can also use this for spelling correction. So defining a query time synonym filter allows us to broaden out the terms in our search query to different terms within the index without making the index any bigger. So this would be one reason why you would want a query time analyzer that's different from an index time analyzer, is index size. So moving right along, let's take a look at some of the other kinds of filters and analyzers that are available just by looking at our default schema setup. So we have an English possessives filter factory that's utilized in a more English-specific text field. There's also keyword marker filter, which protects certain protected words from being removed or from being further normalized. And finally, for this more language-specific version, we have a Porter stemmer filter. The Porter stemmer is best practice heuristic for fast and algorithmic stemming. Stemming takes inflected terms and normalizes them to their common root. This allows us to take words like work, working, and works and turn them into an identical term so that we can more robustly search the term work in our index. So it's important to keep in mind that if there are any special needs that we have in our search solution, that a lot of these existing fields already provide a partial solution for many of them. So one good example is internationalization. So all of these analyzers available are basically really good examples of how we could internationalize a specific field and improve normalization and even sort of tokenization for some of the non-Latin alphabet ones into our index. So one thing to keep in mind is that many of these are off the shelf going to work fine. One of the things that we also have available to us is a folder within our conf folder called lang, and this contains all of the stop words for the language-specific versions. So we have English stop words, and here's actually the standard English stop words for the Lucene stop analyzer. And this is really nice because all of this internationalization is really already handled for you, and all you have to do is define a field that uses one of these languages. There are also a number of languages that Solr supports, but not off the shelf. So make sure to take a look at the Solr wiki and get an idea for what languages are available and easy to grab. And you may have less work than you thought you might when it comes to internationalizing your search solution. Now we have a bit better of an understanding of what goes into creating a text field type and the sort of analyzers, including tokenizers and filters, that really inform the sort of data that's being stored and then the sort of data that's being transformed for lookup against the terms that we have in our index. Field types don't really mean a lot unless we actually declare fields that leverage them. The schema document here declares fields closer to the bottom after all of these internationalized fields. So we have a field node. Under them are the sort of default fields that have been made available for the example search implementation. Let's take a minute to review what has already been provided to us and get an understanding for the motivations behind why those field declarations have been put in place. So obviously, if we are attempting to create unique documents, we need ID that can actually be used to look up a single document. And this field is called ID. It's of type string, which means that any string with any single character difference will be treated as a separate term, regardless of whether there are spaces or anything else. It's from position 0 to all the way to the final end. The entire thing is considered a term. So adding a character, removing a character, strings are pretty much opaque. Now, indexed means that values in this field are added to the index. Stored means that the value can be retrieved. Let's take a quick minute to talk about what stored actually means as opposed to indexed. When we index something, we transform it in a way that is highly performant for the Lucene search engine. However, there often is not an easy way to reconstruct what we have indexed in order to show what we were trying to store in the first place. By saying that something is stored, we're actually saying keep some kind of an intermediary which allows us to recover the actual original value from a state that's not just something that Lucene can read, but rather that a human can read or another machine can read. Finally, required is basically a field that says, if you try to submit a document to me that doesn't have this field, I will complain, and you won't be able to add this to the index. This is pretty useful when it comes to things like IDs, because you really want to make sure that every single one of your document can be uniquely identified, if that is a business requirement for your search engine. Let's take a quick moment to scroll down a little bit more and identify the unique key field, which immediately follows the fields node and declares which field is the one responsible for enforcing document uniqueness. So moving right along, we have an SKU field, which uses a particularly tight splitting English style filter to maintain SKUs, which are kind of like a barcode. These are also indexed and stored. Omit norms is an attribute that is basically used to prevent the normalization calculation in TF-IDF, which in many regards makes a document sort of vulnerable to length considerations. So forward document would have a relevancy of 0.25 if you matched one of the words, whereas maybe a more content-rich document might match that word one time as well, but could have 100 words. So under omit norms, the score would be much closer. Name is a text general. We won't really talk much more about these kind of text general ones. Alpha-only sort is a special kind of text field that is useful for alphabetical sorting, of course. Multi-valued allows us to pass more than one value for the same field and not overwrite or cause any conflicts. So you can have multiple categories, and you don't actually want to put each category into the same field, because then you're not able to do things like group or facet by them. So moving on to other things that we haven't seen yet, term vectors, term positions, and term offsets. These are all particular characteristics of how we track where terms are stored. So again, we're breaking terms up using a tokenizer. Term positions, term vectors, and term offsets all relate to how we identify where terms are in relation to other terms in that field. So, in stock, here's a Boolean one. We haven't seen a Boolean yet, as well as some numeric fields. And these are all just basic, business requirement fields for instance, store that sells electronics, like our search engine seems to be under the example. We also have a lot of common metadata fields here that have been particularly put in order to more easily match up to Apache Tika transformations of web pages to a Solr document. Another thing that is very integrative towards these fields is the Apache Notch project, which is a web crawler. Finally, we have catch-all field that actually gets copied onto by using the copy field declaration. This basically takes the text from a field and appends it to a given field in order to allow us to search against a single field rather than multiple fields. This is done automatically by Solr, which means that you don't have to add additional stuff to your XML or JSON document that you're submitting for indexing, which is nice. Finally, let's take a quick minute to talk about dynamic fields. Dynamic fields allow us to create wildcard field names, which are then matched up to different field types. One of the things I use dynamic fields for is to create internationalized fields using similar declarations. So, for instance, you might want to create a particular field that represents an aspect of an article, if you're doing like magazine search, but maybe you have the article in multiple languages. You might want to have that text stored in different fields depending on which language it is. You can then use these dynamic fields to handle dynamically assigning, based on the language, which field you're actually writing to when you're submitting your document. Now we have a good understanding of what it takes to define what fields are in your schema so that you can index and query the exact information that you're looking for. Now that we have a solid understanding of what goes into our schema, we can easily make changes to our field. So from the comp folder, let's go to schema.xml and find the end of the field node. I like to add schema fields above dynamic fields so that everything's together. Let's create a field called user comments. It's going to be of a general type. We're going to index it. We're going to store it. And it's going to be multi-valued. Now that we have a field called user comments, we actually need something that uses it. So let's go into our example docs, edit iPod other, to add a couple of comments to one of the documents. So, mentioning the field's name is user comments, and then, because it's multi-valued, we can actually write a couple. Note that this is like the cat field above. Grammar is always important with fake comment. So now that we have these comments, let's try to submit them to Solr. We have an error, unknown field, user comments. This is because we never re-registered our schema with Solr. In order to do that, the best way to handle it is to restart your instance. So, send an interrupt, and if you can't do that, then you probably want to do kill all Java or find the actual process and just kill that. And start it up again. So now that we have everything re-registered, let's try to send this out. We've successfully added in the comment. Now, let's perform a query to see that we actually got it working. Alright, note that we have both user comments. Also note that the format in the actual XML response is slightly different from the format that we used in order to send out the field values for these documents. This is just something that you'll have to get used to. However, the CSV and JSON options in the newer versions of Solr give you a lot more leverage for not having to worry about this sort of disjunction. Now we have a pretty solid understanding of what it takes to add to a field and then re-register it with Solr. This is the same kind of thing that we could do if we wanted to alter a field. However, if you have any values in it, it's probably a good idea to remove all documents that include that value so that we can actually avoid corrupting the index or finding any orphan terms that might cause fatal error in your search solution. Welcome back to Getting Started with Apache Solr Search Server. This is Robert Elwell, and this is Section 6, Figuring Solr. In this section, we will discuss the functionality of request handlers in Solr, the purpose and location of default request handlers in the config file, and how to add and modify request handlers. Now that we have an understanding of how to work with the schema.xml, another important configuration component to Solr is the config.xml. We can find this by going to the Solr admin and navigating to the config tab. We can also access this from within the folder that you have Solr installed, the example Solr conf. So I'm there now, and we can look at the schema, or the config file this way. So if we're just browsing, it's probably a good idea just to take a look in the web browser. Here, we'll go through and understand exactly what the config file controls. So as you can see, it's an XML file with a root node for config. Everything else in here is obviously configuration directives. So we have abort on configuration, which will tell us whether or not we should stop loading if we run into a configuration error when trying to start the Solr instance. We have a declaration of what version we're on. And now we have declarations to include different jar files. This basically allows us to invoke particular classes and request handlers that come with the Solr and Lucene libraries. For instance, there are a few analyzers in Polish and things to that extent that you actually need to explicitly require in this area before you can start using them. So that's an important thing to keep in mind. There's also cases where not located directory will be ignored. So again, you can add something in, and if you include a typo, you might not even notice it because it's not going to break or complain. You can specify a data directory that will hold the index data. This is nice because you might be able to put it on a different partition that's mounted You may be able to just put it somewhere outside of your actual Solr install so that you can more easily deploy things. There's a lot of advantages to being able to specify a data directory. By default, it's in the Solr home data folder, which is part of the Solr install directory structure. So moving on, the index config is a major part of what we'll be discussing for this video. The index config basically controls a lot of the behavior around indexing and memory management involved therein. So it's very important to keep in mind that you don't necessarily need to mess with these unless you suspect that something that you're working on is presenting a problem with respect to these parameters. The first thing that you need to be able to understand in order to better leverage these fields, however, is that they exist and that these parameters can be tweaked. So let's take a look and have an idea of what we're really working with for the index configuration. First off, max field length. This is the maximum number of tokens, so not the maximum number of characters, but the maximum number of, say, words counted as many times as they show up in a text document, for instance. A text field, that is. The maximum time to wait for a write block, that's basically something keeping us from competing with resources when trying to write to the index. RAM buffer and buffer docks is specifically associated with handling how we're indexing when we're adding documents and the sort of memory management. These are the kinds of numbers where moving up in one direction will increase speed and moving up in another direction will sort of increase size and might increase your RAM requirements as well. Merge policy is another thing to make sure you have a basic understanding of, and that's basically the approaches that the Solr instance takes to bring together multiple disparate files within your index into a more compressed index. This is more of that fun sort of sparse matrix compression stuff. So, again, merge factor is another component of that. We're going to have possibly a lot of segmented files, and we want to decide how many is so many that we actually need to turn it into one file. This is an expensive maneuver, and that's why, sometimes it's okay to have a lot of different files, and then sometimes we start running into situations where too many files will actually cause more performance and memory management problems than just finally compressing it, regardless of how expensive that can be. The merge scheduler is another component that sort of has a play in this whole dance of the segment files with the main index file. And this is another thing where if you're having issues with scheduling merges, that you may want to consider reconfiguring this to possibly a different class, such as the serial merge schedule. So moving right along, we have some options for locking, so, different file control, basically, depending on what your needs are, whether you want your index to maybe not be written to at a certain time or anything like that. We also have options for deletion policy, so, the amount of commits we may want to delete if, we're deleting at a given point, at a given age, that is. So here's another one, max commit age. We can set, hey, If something is that old, then delete it. And then finally, we have this info stream value, which will allow us to write debugging info to a particular log. Here, by default, it's infostream.txt. And these are debugging info from the Lucene index writer. So, to let you know what's going on while things are being indexed. So, that much is the index config. Now we understand that there are a number of different attributes to indexing that we can control, such as memory management, file merging, and also I/O locking. Next, we'll start to look at request handlers. Another important aspect of the Solr config file to understand is the request handler listings. Request handlers are responsible for directing a URL to a specific class within the Solr library that is then responsible for taking parameters passed to it and presenting back information based on the general purpose of the class. So for instance, here we have a request handler that you can access by going to the select path, and it sends a request to the search handler. So we can access this request handler by going to the base URL for our search solution and then typing in select. You might already be familiar with this from previous videos. So the default query that we often see when we go to the admin is this one. This is actually an invocation of the search handler, which is within the request handler that's pointing to the select path. So all of these are parameters that you are actually sending the search handler, as opposed to, say, a general purpose API. Most of these parameters are specific to the class being referred to here in its given request handler. So it's important to take a look at the wiki anytime you're adding a new request handler to make sure that you're appropriately setting defaults for every parameter based on your business needs. So here's an example of the kinds of defaults that are set. So here we have 10 rows by default. So I could take out the rows directive here, and we would still get 10 rows. Another example is that the default field, df, as a parameter for the search handler, is text. So if I were to type iPod, we would be searching the text field by default, which is a copy field of a number of different textual fields. Other components of the request handler that you may run into from time to time includes appends, which can be used to add in other directives the application or user may not be sending in. Invariants, another way to force certain kinds of behaviors. Here we're forcing every search to perform a facet against the search that you're actually doing. And note that these are commented out, so this isn't actually the behavior that we're seeing. We can uncomment these, restart Solr, and we would get some of these behaviors. And then finally, component list. Components include things like spell checking and more like this, which are actually often request handlers in their own right. Basically, what these do is sort of bubble up the stack and deliver additional information. such as spelling suggestion for a misspelled query or additional documents that may be relevant to the search that you're performing based on the documents you've already retrieved. So now that we understand the architecture of request handler, we can start looking through other request handlers and getting an understanding of what they do. That's what we'll be doing in our next video. Solr comes with a number of default request handlers built in. Let's take a look at what they are and what their purpose is. We already took a look at the select path, which is the search handler. Now let's take a look at the browse path. Note that this also uses the search handler, but a number of parameters have also been set. A response writer has been set using the velocity response writer. Templates and layouts have been specified. A number of different parameters have been set in order to perform default boosts, default filtering, and default faceting. Let's see what we get when we actually navigate to the browse path. As you can see, this is an example of the kinds of things that you can do within the velocity response writer. The idea here is basically that you can work directly through Java using the templating system made available and the layout system in order to use this browsing library. Personally, I find that most of the projects I've worked with would not be able to use something like this, but I'm kind of a PHP guy. You may be a Java person, and this might be a great opportunity for you to get started really quick with an application that's just looking for some basic search. So, the browse component, which uses the search handler class, is basically sending your searches through a templating system in order to give you that pretty user interface. Let's keep on going. The update request handler is responsible for accepting stream that contains the update XML. So this is where you're sending your adds and deletes to as your member. There are a number of sort of sub-request handlers to handle different formats. So the regular update path uses the XML update request handler to accept XML. However, you can accept binary, you can accept CSV, you can accept JSON. There's a number of things that you can use. So, moving right along, the analysis request handler, you may remember, this is what you get to when you click the analysis tab. And this allows us to get an idea of how a field is being analyzed. The admin page is also a request handler. It's the Solr admin handler class. This is actually an abbreviation for a whole bunch of other request handlers all rolled into one. The ping request handler is good for performing automated health checks. If you have a very ops-heavy backend, this might be something worth implementing so that you can monitor and make sure that your solution has not frozen or has not gone down at any given point in time. There is a debug request handler that will dump back the contents of your request. Replication is performed using its own request handler as well. So if you need to replicate from one server to another, this is the place to start looking and reading. The idea is basically that you want to pull from a master and then basically pull down the master's index. If you're using replication, it's generally a good idea to keep the master away from performing any kind of searching and let it just handle indexing and sending over the index to its replicants. Spell checking is a component which can be used. However, you can also make a spell check request handler. So, here we are with the spell request handler. The term vector component allows you to get a feel for what terms are in a given document. We can take a look at it from here. So, let's see what we can do with that. We can say text iPod, and we get a response, and then a list of the term vectors available. This is useful because it lists the kinds of terms that are showing up in your indexed and stored fields. It will also tell you what the unique key is for a given document. Clustering allows you to do some interesting grouping and learning over your data. We will not be covering this in our exercise. The terms component will list a set of terms for a given document or a given query. So we can say, I want to look at all of the terms for the exact manufacturer field, and we have a list of the terms available and the counts in the index. Note that if you have a very large index with a lot of terms, this is going to be a very expensive query to make. I wouldn't suggest doing it on a production available index. The elevate request handler is capable of letting you specify what documents should be pushed to the top for a given search query. I personally find that this is a very difficult component to use because you never know if the query that you're sending to Solr from your application is going to be the right query, particularly when you need to work with relevance. You don't necessarily want to have to keep rewriting queries and then hope that the elevate component works. I highly suggest performing elevation within your application logic instead, if you can handle it. So now we took a look at all of the request handlers available to us, and we got an understanding for what they can do. In our next video, we will write our own request handler based on an existing class in Solr and see how to utilize it. Now that we understand how to use request handlers, we can implement our own based on some of the existing classes that have just not yet been invoked in our solrconfig.xml. So, let's go to the Solr wiki and take a look at the more like this component. The more like this handler allows us to send a document by a query and get similar documents based on the interesting terms within that document. So, we have to add a request handler into our config before we can use these examples. So, first off, we modify our Solr config. Then we send an interrupt to our process and restart Solr. Now let's take a look. So, as you can see, we added in a node to the Solr config, specifying that the MLT path would direct us to the more like this request handler class. We did this by navigating to the wiki and following the exercises there. And then we actually clicked on the links in the Solr wiki to take a look at some of these example documents using the more like this request handler. This is important for us to understand because it means that whenever we want to learn a little bit more about Solr, and whenever we want to try to add new functionality that we know Solr has to our application, there is a lot of great material out there that we can just study and work with, and even, have links to our very own instance within the wiki so that we can really get a feel for how we need to do this before we have to implement it on our production instance. This is a really, really strong feature for the Solr project's documentation, and that's why I strongly encourage anybody who is working with Solr to very carefully study the wiki, because you don't know how much is available until you do, and you don't know how easy it is to implement it unless you take some time to read it. So now that we have an understanding of what it takes to write a request handler into your config and implement it, we can fully customize solution for our very own business needs. Welcome back to Getting Started with Apache Solr Search Server. This is Robert Elwell, Section 7, Solr in Practice, a Use Case. In this section, we will discuss an example use case for a web application that relies on Solr. We'll learn how to identify the appropriate format for the document schema based on our business requirements. We'll learn how to use faceting in a search-based web application. And we'll use the more like this component functionality for text-based recommendation. So it's sort of a culmination of everything we've done so far. Let's create a business case and implement it using Solr as our back-end solution. Our toy example here will be a beer site where we search for beer reviews, and then we can compare beers and find other beers by the same brewer. So I'll be using the Open Beer database, which is free with no rate limit, so you're welcome to follow along with this example. I have all of the code here on GitHub, github.com/rlwell/beersite. It's totally available to fork or to just inspect. So first off, a little bit about the actual API we'll be using. We'll mostly be working with this beers service that has the following set of data: ID, name, description, ABV, which is alcohol by volume, not something that we'll be implementing for this example, and then creation update dates, not really something that we need either. Then finally the brewery ID and name. So this is going to be pretty useful as well, because one of the things we want to be able to do is find other beers from the same brewer. So the first step to use this example is to clone this Django site into any folder, because we don't really need to put it through Apache. It will be serving up localhost at its own port using the manage.py script that comes with any Django site. So git clone and then the .git file on GitHub. Then we can go into beer site here and take a look at what we've got. So first off, I've included the library Pint, which is designed to interface with the open beer database. We've also got a folder called Solr Files. That contains the Solr schema that handles our use case pretty well, and we'll go into that in a later video. We also have a script called importbeer.py, which uses Pint to feed data into Solr using the schema here. Beer site is the actual Django site that serves up the different sort of controller actions that we'll need in order to accomplish what we're doing. So my suggestion would be first to unzip another copy of Apache Solr. This way, you're not overwriting anything you've already done with the other example. I'm renaming it Apache 2, just to make it easier on us. Alright, so here we are. We go back into the example folder. And the first thing you want to do is copy the schema.xml folder from the GitHub project to the new Apache Solr in example Solr conf. So now we can start our Solr instance. Thing is loading up. And now let's take a look at the importbeer.py script. This is what one might call an ETL, or extract, transform, and load script. We connect to Solr. We select all beer instances available from the API. We see how many we got and tell standard output, hey, this is how many beers we have. And then we basically create a list comprehension that builds out this data type, a dictionary containing ID, name, description, brewery ID, and brewery name for each beer, such that we can submit this list of dictionaries containing these fields and values to the Solr connection. And then we commit the changes, because this particular library doesn't commit automatically to Solr. So let's run that and see what we get. Found 60 beers, successfully imported documents, and if you'll notice, the logs for Solr also let you know, oh hey, we just got commit and some updates. So let's take a look at what's in our Solr instance right now. Looks like a lot of beers, right? So now, let's do our first search on our Django site. We go into the beer site folder under the beer site folder and take a look at our views. We've got a home page with a search form. We have a search page that shows search results. And we also have brewers and more beers like this. So in order to access this site, we type python manage.py run server, and then the port that you want to run it on. I'm going to use 88. So now we can go to localhost :8080, and we have the beer search site. I like a beer with hops in it, so I'm going to search for hops. As you can see, we have a fully fleshed out website with a lot of different approaches to showing beer. We have faceting, we have by brewer, we have more like this, and we're also including some information from the document, such as the review, the title of the beer, and the brewing company. We'll go into what our business requirements were and how we accomplished them in the videos to come. Now that we have our site up and running, let's take a minute to get a feeling for how we created our schema and the reasoning behind it. So first off, let's go back again and take a look at the data available to us. We have a beer name, beer description, and we have information about the brewery. For our use case, we want to be able to do three things. We want to be able to search for a beer based on its name, description, or brewer, and get a match. We want to be able to see all of the available beers from a given brewer, and we want to be able to group beers together based on similarities. So if I find a beer that I like in the search results and I want to see similar beers, I should be able to do that. So let's take a look at our existing schema so that we'll understand what exactly it is we had to do in order to accomplish this. So, taking a look at our schema.xml file, we have ID, and that's type string because the unique key must be of a string type. We have the name, so that's the name of the beer, and that's a text general. This could also be text English. It doesn't really matter. In fact, we have a copy field called text, which is of type text English, that actually includes these text general, description name, brewery name copied over for better analysis. We're also including brewery name, which, as you'll see, is as type string by itself. And same thing for brewery ID. So the idea here is that because we want to be able to group things by similar brewery name, if we were to use faceting against regular text, then it would facet against each token rather than each single term. And brewery name, regardless of how many spaces, should be considered a term because it's its own entity, as opposed to words, really, which serve as separable terms in a body of text, right? So, now that we understand the actual composition of the schema, we can take a minute to talk about the text field. The text field is actually the field that we'll be searching against anytime we enter a search, and this is what allows us to easily grab any value without having to specify. So for instance, if I wanted to search for a beta brewery, now I'll have all results for a beta because they are all going to be matches. If I wanted to find something that had the term continental, I don't have to make any change. I can just search against the copy field, and we'll be able to find it. We can also perform a search for the name. So, bet you there's one that's a stout. Here we go, Alaskan Brewing Company's stout. So, as you can see, using a copy field allows us to be able to search against multiple fields at the same time. Just make sure that you set your copy field to multi-value, or else you're going to run into trouble. Now that we have an understanding of how our schema affects our ability to search and group, we'll be able to look at the other use cases aside from searching. So you may have noticed that up at the top we have this piece of text, brewers matching your query, and then a whole bunch of brewery names, and then numbers in parentheses. How do we get these, and what do they mean? Note that depending on what gets matched in your search results, the numbers here change. This is called faceting, and it basically tells us, hey, we have our results grouped by this different field in your schema. So that's accomplished by sending a faceting directive during search. So looking in the beer site views folder, we can see that in our search view, we're passing along to our Solr connection a query, and then the options to facet and facet on brewery name, which is one of the fields that we define in our schema. Let's take a look at the search results.html template that we're using in order to feed out all of our data. So that's in the folder templates, search results.html. So we'll start off with a little style, and now we're down into the HTML. The first thing we show is our form. Then we move down, take a look at if we have search results, do we have facet counts? We iterate over each facet. So the response is going to include a facet counts field, a facet fields field under that, and then brewery name facet field, because you can ask for multiple facets. And then we're going to iterate over all of the items in that dictionary to show the brewery and the count, because key in the dictionary is the brewery name and the actual value for that key is the count. So faceting allows us to add in links to a brewer. So if you want to click on a brewer and view all of the beers from that brewer, all we have to do is perform a different search in Solr. This says, hey, let's search for whatever term has been passed to this RESTful URL. So anything after brewer is being parsed as an additional variable that is passed to the brewer's view, and then we basically use that to search. Note that we really haven't put much effort here into, for instance, validating or filtering. So this is definitely not production-ready software. But now, our searches include anything that matches that string field. If we were, for instance, to make the brewer name general text field, then we would actually have to worry about other brewers creeping in that had one or two identical terms in a multi-word. So now that we understand how faceting works, take some time and do a little homework. See what you can do about making the regular search approach also accept a term for actually filtering your original search by brewer. This will use filter queries. So optimally, if you have a count for something matching your query, you should see that many results when you're searching for that given brewer while staying in your original search term. The final use case that we haven't yet looked at is the more beers like this option for a given search result. First off, let's take a look at how this is accomplished in our Django site. We have a view called more like this, which is routed to a URL that has more like this, and then the ID of the document. So how does this change the actual query that we're performing? Well, so instead of searching on text, we're actually just saying we want the document matching this ID. We're only going to get one ID for that. So then we also have to pass the MLT parameter, which is standard on the example request handler, to accept. And then we tell it that we want to match on the description field. So what the more like this handler does is it computes what the interesting terms are for your document set and then searches against those interesting terms in order to determine what the result set should be for a more like this search. So from here, we can click on the more like this for stout and see what we get. First, let's inspect the actual text from the description so we know what to look out for when we're inspecting the new set of results. We have a unique blend of oats and malts, producing a balanced, smooth beer with hints of coffee and caramel. So my guess is that the things that we're going to get matches on will probably be things like coffee, caramel, maybe balanced and smooth, perhaps oats and malts. So, a lot of content. Beer, probably not so much because it's all beer on here. Hints is probably a word that's going to get thrown around a little much. The rest are mostly stop words. So let's see what we get. Okay, so balance. We have hops, and that was on there. Hops. Malts. So you can sort of see that there's a little bit of prose here that makes sense that these are grouped together. Let's try this one. It's got a lot of interesting words. Velvety, sweetness, creamy finish. Let's see what we get. Okay, well that's interesting. The top one is finish. So finish must be a interesting term because it's probably only in these two documents that we're seeing, which makes it rare from inverse document frequency standpoint. And because they're both short reviews, they actually have a high term frequency for those given documents. So that's kind of what the more like this handler generally capitalizes on when it says that it uses interesting terms in order to build out its search results. Another thing to keep in mind is that we're actually accessing the search results from the more like this request handler with the single response for the query that we made, and then actually accessing separate value when we want to look at the similar results. So what we have here is a title that we're setting because we don't really know what we're doing with the same view over and over. So we set the title in the view. And our first result, we're actually feeding out the name and the brewery name to make it say more like beer name from brewery name. And then we iterate over our search results. Now we understand how to use the more like this component of a search. This gives us a lot of ability to implement easy recommendations and bring similarity in without having to do expensive calculations. So much of the work is done for you that there's almost no reason not to implement it on a basic e-commerce site or anything else that includes useful text. Welcome back to Getting Started with Apache Solr Search Server with Robert Elwell. This is our final section, Section 8, advanced concepts. In this section, we will discuss grouping results in our sample web application, using the highlighting component for Solr native snippets and highlighting, how to implement Solr's spell check component, and advanced usage for the more like this request handling. We'll now be examining some more advanced approaches to using the Apache Solr Search solution. We're going to build off of the example site that we were using in the previous set of videos. So, if you have already pulled down the beer site code, you'll notice that there is a branch called Advanced. Advanced contains 4 commits that follow the videos that we're going to be reviewing. So, what I would like to do is kind of start at the first commit, which is what we'll be looking at now, and then move forward over time so that we don't look at too many things at once. Because in the end, we should have the aggregate of all 4 of the changes that we're making. This video focuses on group search results. So, how do we implement group search, and what exactly does that mean? So, first off, let's start our Python server again. Just in case we forgot how to do that. Alright, so now that our site is running, we can navigate to it. Alright, so as you can see, we have a group button, and we can search for hops, and say we want to group it, and now our results are grouped by the different brewing companies for matches on the term hops. So let's take a look at how we made these changes. Okay, so going into the beer site folder, let's take a look at the views file. Here we are in the search view function, and as you can see, we have added a few additional parameters to the search query. Group equals true if the button, the checkbox was clicked for grouping, and false otherwise. Note that we're setting the strings true and false, and not the native Python scalars true or false. And then we identify the field in the schema that we want to group by. And then, unless we pass a group limit value, we will actually be only returning 1 result per grouping. So if you run into that, make sure that you have been explicit about your grouping limit. So how does this work in the actual template? Well, first off, we have to decide whether or not the groupings were passed along. So let's take a look at the template now and see how passing along grouping helps us. So, on our way down, we are at the search results iteration, and here we say if we are grouping our results, we'll use this partial. Otherwise, we'll use a refactored version of the old search result markup. So what does this look like? Well, search result.html is what we were used to before, but grouped search result actually contains something different. So first off, we have to get our variables in the right scope. And then we actually are nesting in the search result template that we were skipping using in the main search results template. Note here that we are using the group value of the result. And note that in order to get these correct values, we actually have to identify the appropriate component in the search response that we want to be iterating over. So, the search results model for this Python package actually allows you to iterate over the proper field if you only want default search results. Otherwise, we are specifying which list we want to iterate over, which is the grouped brewery name groups field. So, now that we understand how to do a grouped search, we could do all kinds of different groupings. For instance, if we wanted to group over, instead of brewing company, perhaps alcohol percentage by volume. This might not work so much for the craft beers because they're a little bit more variable, but if you had domestic beers in here, it would probably be nice to know which ones are, 4% versus 3%. But in any case, this is very applicable to a wide range of business needs, and now you know how to do it using Django, so you can get a feel for how to do it in your own enterprise application. Another useful feature that we would like to see in our beer site is the ability to highlight matches for our search term. So, we have hops here in this result, and we would like to have this italicized or made bold or give it some other kind of treatment that requires putting markup in the description field. Now, you could search for a term and then attempt to do a string replace. However, we would run into problems in the naive approach when it comes to inflection. So, if I were to search for hop instead of hops, I would get the same results, but using the naive approach, we would only highlight the root of the word rather than the whole, which looks kind of confusing. Because Solr includes information about where terms are in a given field, we can actually implement highlighting native to Solr's capabilities. In order to take a look at this code, I suggest checking back out the advanced branch and identifying the appropriate commit in the history. It should be the implement match highlight. So git check out this commit, and now we have some capability for match highlighting. Let's take a look at what's going on under the hood before we make any kind of queries. So we're looking at views.py, and you'll note that a number of changes have been added into the search parameter. First off, we are specifically identifying which fields we want to search over by using the QF parameter. This stands for query fields, and it allows us to list where we want to search for our terms in a document. Originally, we were searching over the copy field text by default due to the off-the-shelf settings of the search handler in our Solr configuration. Because we want to highlight the description field, however, we need to specifically instruct Solr to search against it. Otherwise, we risk not getting the results that we want in the highlighting field. So we have set the highlight parameter to true, which will cause an error unless we specify the highlighting field, which is our description field. And here, because we want to use the entire description, we've set the highlighting fragment size to its largest possible size. Pretty sure that this has to do with characters, but in many cases, you may not need this if you're searching over very large documents. So, another thing that we're doing is iterating over the search results highlighting grouping, and for each search result, if there is highlighting in the description field, then we assign that to be the results description. Otherwise, we reassign the results description to be its own description. That's just a bit of a hack to get it all in one. So, let's take a look at how this works in the wild. So, I search for hop, and you'll see that we are italicizing the correct stuff. Also take a look at yeast. And again, italicizing yeast. Now we know how to introduce highlighting into your search application. This helps users get a feel for what makes the documents that you're showing them in the search results page a relevant result, which improves user experience and makes your application feel more responsive. Another method of introducing robustness into your search solution is to use spelling correction. Very often, your users will be prone to typos or misspellings. In order to provide them with the best possible user experience that you can deliver, it would be a good idea to use the data that you have within Solr to provide suggestions on what a well-formed search term may be in your dictionary. Solr has native capabilities for handling exactly this issue. In order to use them, first, check out the head commit of the advanced folder, and take note that we have a copy of solrconfig.xml here. Copy over that configuration to whatever location your example folder is for Solr. It should be someplace like this, example/solr/com. Now, let's take a look at what exactly we changed. We've updated the default search handler right here to include a last component of spell check. So this utilizes the native spell check component within the search handler. So make sure to restart your Solr instance by sending it a Control-C, and then, once again, calling start.jar. And now, let's check out only the commit that adds in spelling suggestions so we can see changes that in order to accomplish this. Let's take a look at what we have here in the views file. So, as before, we have the query fields, the facets stuff, the highlighting stuff, and the grouping stuff. And now we're including 3 parameters to handle spell check. By passing the string true to the spell check parameter, we're telling it that we want it on. And that will put into the response spell checking information. By telling spell check to build, we're telling it that if it does not have a dictionary, to build one. If you don't tell it to build, then you're not going to get search results back for spell check. If you need to reload the dictionary, note that there is a parameter specifically for reloading, so build only really works once. Finally, spell check collate tells spell check to take all of the suggested terms that it has, pick the best one for each one term that it's spell checking, and then group them together. An example for this would be a case where somebody types in great places to eat in Cincinnati, and we're actually getting back from Solr a bunch of different lists. So you would get something back like this. when what you really want is the collated version that even includes the spelling corrections. Of course, nobody's perfect. So with that in mind, let's take a look at how we handle our spell checking information. First off, we look and see if we received suggestions in the response from Solr, and if we did, we check and see if there's anything in the collation group. If not, then we set spell check to false, and then in the view, we just skip over it. Let's take a look at how we handle this. So as you can see, we have at the top of our wrapper for all of our search results a did you mean span that URL encodes the spell check string value to be sent along to a search, and then of course just the regular spell check value in the anchor text. So let's give this a try with stout. Let's misspell stout by transposing the U and the O. Now it says, did you mean stout? And we can click here, and yes, I did mean stout. And there is the stout. So now we understand another method of introducing robustness into our search application. This one is particularly applicable because it handles the chaos that is bringing your application out into the user-facing world and setting it loose upon your users. A final little brain teaser that I thought would make a useful lesson for anyone who is serious about working with Solr is using the more like this request handler to find the interesting terms for a given document. Why do we want to know the interesting terms in a document? Well, the answer is quite simple. Interesting terms don't just mean what's the strongest term in this document, but rather what terms make this document interesting relative to all other terms. This means that we can use this capability for discovery and interesting feedback on your index. First off, we can now finally check out the head of the advanced branch and really mean it. Here is where we have the updated schema for the request handler. If you already did the previous exercise, which includes moving the Solr config file over, then you should be set. Otherwise, make sure to copy over the Solr files to the appropriate place in your Solr instance. If you don't know where those are yet, go back through the videos, because you should know by now. So, let's take a look at the changes that we made to the Solr config in order to accommodate the more like this request handler, which is not a native request handler. This is very simple. We're basically saying, point this path, MLT, to this class. There's really no other configurations that you have to pass over in this bit of XML. So let's take a look at how to use it. You have to include a query, which will provide you with the appropriate document. And you also have to specify a field that tells Solr what fields to perform more like this over. If you don't provide the field, you'll get the error that you just saw. So here we have the result based on the ID, and now the actual more like this results. So you'll note that there's a result with the name match, and then a result set with the name response. But what we really want to know is, what made that first document interesting? So we say mlt.interestingTerms equals list. Now we've got match result, response result, and interesting terms. Now, note, because we're using an aggressive analyzer that includes stemming, we're losing a little bit of information. We're losing the E at the end of ale. We're losing S for hops. I don't think that we run into hop anywhere, but we have hops everywhere, as it were. So that's one of the things to keep in mind. This is still a super informative list of terms, and they are in rank order. We can get additional detail by selecting details instead of list for the interesting terms parameters. And these are basically the boosts that these terms have presently. There are options to set the boost in sort of a first term gets the most and then the following term gets less and less and less in order to better weight the more like this results. But that can be a little advanced for the general purpose need. I think that the big benefit from this is to be able to look at any document and immediately find out what's motivating Solr to say it's a match for certain things, to say it's highly relevant for certain things, and to say that other things are relevant to it from a similarity perspective. And now that we have this, anytime somebody says, well, why did this result show up? We can look at two things. We can look at the debugging information from a regular search query, and we can look at the interesting terms from the more like this request handler, and give a very accurate description of how that document interacts with the rest of the document set in the index, and how that causes relevance to shift and move. Now that we understand the interesting terms portion of the more like this component, we are a little bit more prepared to speak to stakeholders about the strength of TF-IDF, and specifically how Solr uses it in order to deliver us relevant results.